And the object distance is the distance from the mirror or the lens. We'll be dealing both with mirrors and lenses, but you'll see that they're largely the same. So it's the distance from the mirror or lens to the object. So for example, if you stand in front of your bathroom mirror, the distance from you to your mirror, that's your object distance. So if I have my bathroom mirror and I'm standing here in front of it, this distance is my object distance. The image distance, on the other hand, is the distance from the lens or mirror to the image. From the mirror or lens to the image. So if you imagine your image is back here, I'm a little bit taller in my image, then this distance is my image distance. All right? So my object distance and my image distance are just the distances from the mirror or lens to either the object or the image. We usually call the object distance P, and we call the image distance Q. As I said, this is the distance to the object, and this is the distance to the image. We have some criteria or from some notations that we take for Q. If Q is positive, then the image is a real image, and real images can be projected onto a screen. The cornea and the lens in your eye, that produces a real image. It actually projects an image onto your retina. This is a real image because I can project it onto a screen. It's an actual image. It sits here, and I can project it onto a screen. That only occurs mathematically when our Q, our image distance, is positive. If Q is negative, the image is a virtual image. And while you can see the image, you can't project it onto a screen. So up here, for example, with our bathroom mirror, that type of image right here, this is a virtual image. Because you can't project that image onto a screen like you can, say, with the lens in our projector. All right, so we have real and virtual images. Real images have a positive image distance. Virtual images have a negative image distance. If Q is greater than 0, that's a real image. If Q is less than 0, that is a virtual image. You can still see the virtual image, but you can't project it onto a screen, like in your flat mirror. And we'll see some other virtual images as well. We're going to look at several different optical devices. The first will be the flat mirror. It's the easiest, so we'll deal with it first. There's really only one rule with flat mirrors, and that is just that Q is equal to negative P. So what kind of image then, if Q is equal to negative P for a flat mirror, that means my object distance will almost always be positive. We'll see one case later where it's not, but my object distance P is almost always positive. That means that my flat mirror is always going to produce what type of image? A real or a virtual image? It'll produce a virtual image because Q will always be negative. So it produces a virtual image, and not physically because, but mathematically it works out because Q is always negative. We're going to skip the Feynman clip there. It was just sort of for fun. All right. So that's really all we need to know for flat mirrors is that the image distance is equal to the negative of the object distance. So if I'm at one side of a flat mirror, this distance will always be equal to this distance. Q will always equal to the negative of P. And the negative really is just there to tell us, is this a real or virtual image? We're also going to talk about magnification. We'll talk about magnification with mirrors and with lenses. It'll come up quite a bit. With a flat mirror, what's the magnification? Do you look bigger, smaller, or the same size in a flat mirror? You look the same size, right? And so you would say that the magnification of that mirror is equal to what value? it's equal to 1. So you sort of have an idea of what magnification is. If you make something appear bigger, then the magnification is bigger. So if my mirror makes me look twice as big, then it has a magnification of 2. Use that with microscopes and telescopes as well. Or you can make things appear smaller, and we'll see some mirrors where you actually make things appear smaller, where you have a magnification less than 1. We can define the magnification in a couple of different ways. First, we can just compare the size of the object and the image. And so that's going to be the image height over the object height. The image height over the object height. Usually we call this HI over HO. And a magnification of 1 means the image is the same size as the object. A magnification greater than 1 means the image is bigger than the object. And a magnification less than 1 means the image is smaller than the object. And if the magnification is negative, whether it's bigger, equal to, or smaller than 1, if the magnification is negative, that means that the image is inverted. All right, so in this case, the image height is also negative. So if I have an object right here, and I have an image right here, how would you describe the magnification of this image? First of all, is it bigger, the same, or smaller than 1? The magnitude of it is smaller because the image appears smaller. And is it positive or negative? Negative. So this looks to be about half the size of the object. So I might say then that the magnification of this object is equal to negative 0.5. Negative because it's inverted, and 0.5 because it's smaller than the object. All right, so that's magnification. It's going to come up. Part of your test, you'll have a question where I give you some optical system, and I ask you, what is the magnification? And sometimes that's a simple thing, and sometimes it's a little more complicated. But we'll work through some example problems to show you how to do that. All right, let's see. Okay, I don't know what that is. That was a holdover. This is just sort of a summary of what the magnification means. We've already seen this, but you'll need to know all these notations. That if it's bigger than 1, it's a bigger image. If it's less than 1, it's a smaller image. If it's equal to 1, it's the same size. If it's positive, that means the image height is also positive and it's upright. If it's negative, that means it's inverted. So you might want to put that on a little note card and just sort of remember those, because knowing those notations will be very important for the exam, the couple of problems that you'll have on the exam. All right, so there is also, I have this relationship with HI and HO. There is also a relationship for magnification that we'll use more commonly that's based on the image distance, which is Q, and the object distance, which is P. Now, based on what you know about the flat mirror, what would you say is the magnification? The flat mirror, we said that Q is equal to negative P. So how would you find the magnification if we know that it's some relationship between M, Q, and P? How would the magnification be related to the image distance and the object distance if I know also that for a flat mirror that Q is equal to negative P? What are your thoughts? It's hard coming back, huh? Is it hard? All right, well, if Q is equal to negative P, then it shouldn't be a big reach for us. And it works out through geometry. We're not going to go through it, but that the magnification then is equal to negative Q divided by P. Right. That doesn't derive from the flat mirror, but I know for a flat mirror that Q is equal to negative P. And if that's the case here, then I get a magnification of 1. If Q is equal to negative P, I put in a negative p here, then I would calculate a magnification of 1. And so this is our expression for the magnification, and this is too on your equation sheet as well. Now for images and flat mirrors, we have these rules. First of all, Q is equal to negative P, which we've already said. That tells us that the image is virtual, and also that the image is behind the mirror. This is another idea that will be important to answering questions as we move into those later in this chapter. But anytime I have a virtual image, it's going to be on the so-called virtual side of the optical device. And for mirrors, that virtual side is on the back side of the mirror. You can remember this. Just remember that flat mirrors always produce virtual images. And, where is the image in a mirror? Well, it's on the opposite side of where you're standing. So virtual images will always be behind the mirror. Anytime I have an object over here, the virtual image will be over here. That's true for flat mirrors, but it's also true for curved mirrors. And we'll see with curved mirrors that I can either have real or virtual images. Now, where would the real image be on a mirror? Would it be on the opposite side of the object or on the same side as the object? Where would the real image be? Now remember, what defines a real image? How do we define what a real image is? You can project it onto a screen. So where must the real image be for a mirror or for a curved mirror? On the same side as the object or the opposite side of the object? On the same side, because you can't put a mirror behind the, or you can't put what is it, a screen behind the mirror, okay? Unless you're like in the Poltergeist world. You ever seen that movie with the creepy lady? Come to the light. You ever seen that movie? It's like from the 80s, I think, but I think it's made a comeback. You've seen it, right? Yeah, okay. All right, where all the people are in the back side of the mirrors. Okay, and then also for flat mirrors, m is equal to 1. That means the image is upright. And it is same size as the object. We haven't really said much that's groundbreaking. We're just sort of laying down some ideas. You have our image distance, our object distance. We have our magnification. The magnification is the image height over the object height. If the image is bigger than the object, the magnification is bigger than 1. If the image is smaller than the object, the magnification is less than 1. We've also brought this idea that the magnification is negative if the image is inverted. So if our magnification is -1, that means our image is upside down from where the object is. Your eye, by the way, produces an inverted image on your retina. We'll talk about that later. All right, so not really much so far, but let's look at, let's look right now at ray diagrams. So when drawing your ray diagrams for a flat mirror, we need to use something called the law of refraction, or excuse me, the law of reflection. And the law of reflection just says that the incident angle is equal to the reflected angle. This is true for particles too. Like if I have an object and I throw it, it bounces such that the incident angle, that's this angle, theta I, is equal to the reflected angle, just theta r. That's true for light. It's also true for particles bouncing, like for example a pool ball bouncing off of the bumper of a table. All right. If we want to locate the image, we draw a ray from the object to the mirror, and then the ray reflects according to the law of reflection. So I can draw a ray that comes from this object. So this is an object, this is a mirror, and I want to figure out where is the image of this object. And so in order to do that, I have to draw two rays. Now, there are software packages that actually draw rays for optical systems, but we're just going to do them by hand. Those of you that go into graduate school, like if you ever build an optical device, some sort of spectrometer or whatever, you have to plan out your optical, what are the light rays as they travel through this optical system. And you geomatics folks might have to do that too. I don't know. Do you guys folks do that? No. You might later if you go into a graduate program. But we can trace out our rays here. So the first ray I draw from the object, and I know that the incident angle is equal to the reflected angle. Then I can also draw a second ray. Say I draw a ray that comes like this at a different angle. So rays are emanating from this object in all directions. So I drew one ray that comes down here, and then I draw another ray that comes down here. Now in reality, there are many, many rays that are coming in all directions, but I've just picked two to draw. This one is also going to follow the law of reflection. It'll look something like this, because these two angles have to be equal. Now, to determine where the object is, I have to find the place where two rays cross. Now, notice these two rays, the reflected rays, are they convergent or divergent? Are they going to come together or do they never come together? They never come together. They're divergent. They keep going farther and farther apart. So they're never going to create an image on this side of the mirror. They're never going to create what type of image? The same side as the object? That's a what type of image? That's a real image. Instead, they're going to create a virtual image. And to figure out where the virtual image is, we trace the rays back. I trace this one back. And I also trace this one back. And that tells me where they cross, where the image is. So the image of my star is going to be right there. Now, I haven't done it very carefully. It should really lie right across from the other star. It's pretty close. This is my distance, my object distance. I call that P. This is my image distance. I call that Q. And I know for flat mirrors that P should equal to negative Q, that those two distances should be the same. Next semester in lab, you'll do this where you actually trace out these light rays. But we're not going to cover this material next semester because we move on to something else. Okay? You with me so far? Yeah, it gets a little more difficult from this, but not a lot more. Let's try this little quick test. This figure shows two people that are observing the image of a rock in a flat mirror. This is the rock. These are possible images. Where does person number one, or rather person number two, this person, sees the image right here? Where does person number one see the image of this object over here? Where does this person see the image of that object? Okay, we're sort of all over the board. I'm going to give you just a few more seconds. I'll stop at 102, 102. Right, a lot of you put E, and that is sort of the common misconception. But the fact is that it doesn't matter where you are, that the image of this object will always be the same. That my image distance is always equal to my object distance, right? And it's always going to be directly across from the object, right? So it doesn't matter where you're standing, the object distance will always be the same. The image distance will always be the same, right? Let's try this next one. What is the magnification of a flat mirror? Right, I'll stop at 20, 20. Okay, good. A is right. The magnification of a flat mirror is always equal to 1. It's always equal to positive 1 because it's upright, and the object is always the same size as the image. Let's see, I don't have a joke for you, but I have just an interesting thing that I learned. Did you know that the speed of time is 1 second per 1 second? Don't know that? It's interesting, isn't it? All right. All right, so the answer here is 1. All right, we're going to look at spherical mirrors. They get a little more complicated, but we're going to see a lot of the same notation. And this is more of what you'll see on the test for spherical mirrors. But we'll still see our P, we'll still see our Q, we'll still see our magnification, and it'll all work out largely the same. You need to keep in your mind those notations that if Q is negative, that's a virtual image. If M is negative, that's an inverted image. Spherical mirrors, we can think of them as being cut out of like a big spherical reflecting surface. So just imagine that I just slice off part of the sphere, and then I take that spherical part of it and make a mirror out of it. Let's see, I have a couple of spherical mirrors. You can imagine that these are just sort of one part of a big sphere. So see, this is a spherical surface, and it's like it comes from a much bigger sphere. You don't see yourselves in there? How do you look, by the way? Is your magnification positive or negative? It's negative, right? Because you're upside down in this, that means that your magnification is negative. Brennan, can I put it up close to you? Is that okay? Is your magnification bigger than 1 or smaller than 1? Bigger, right. This is like a makeup mirror. It's like a huge makeup mirror or a shaving mirror. And when you look in it, you look a lot bigger. It helps you to see sort of all the pores and the dirt on your face, which we all have, right? So you have one of these likely, or you might have one in your house. By the way, if you look at that mirror and you go really far away from it, you'll eventually turn upside down if you can see yourself. So try that out. It's just, you don't usually see it because that mirror that you have in your bathroom comes from a much bigger sphere than this mirror. This is a smaller sphere. Okay, so if the inner surface of the sphere is reflecting, that's just like this one. The mirror is a concave mirror. And I like to think of this, the concave mirror, where this is my reflecting surface, that my reflecting surface is over, rather, that my object would be over here, and this is the back side of the mirror. And as I said, this is like a shaving mirror or a makeup mirror. And just to begin thinking about these, because you'll need to know what type of mirrors produce what types of images. I'll repeat this later, but let's go ahead and start thinking about this. Goodness, Sadie, bless you. That if you're close, image appears big and upright. If you're far away, image is inverted. And it may be big or small. It sort of depends on the mirror. We'll figure out how to do this mathematically later in the chapter. But just for now, begin putting this in your mind because it'll be important that you know what types of mirrors produce what types of images. The next type of mirror is a one where the outer surface of the sphere is the reflecting surface. Um, so on this one, this would be the back of the mirror. And your object would stand over here. Where have you seen mirrors like this? This is called a convex mirror. Whereabouts? A security mirror. So like, I don't know, in stores or whatever, I have one. You've seen them. This one's a lot like the ones that you've seen. You also have them in your car. The passenger side mirror on the side is usually a mirror like this. It's not this big, I guess. Maybe it is. But it's not usually this big, and it's not usually so obviously spherical. But if you look at it, it is spherical because things just look different in that mirror. They look smaller, much like you guys look smaller, right? Do you look smaller in this mirror? Yeah? What is the magnification of this mirror? Is it positive or negative, first of all? Positive, because you're all standing upright. And then also, is it bigger or smaller or equal to 1? It's smaller than 1 because you look smaller than you actually are. Okay, this type of mirror is called a convex mirror. The convex mirror, an example, is like a security mirror or the right mirror on your car, passenger side mirror. And it always makes things appear smaller and upright. So images are always smaller and upright. That means that m is less than 1 and m is positive. It's less than 1, so they're smaller, and they're upright, so it's positive. So it's somewhere between 0 and 1. Okay? For both types of mirrors, we're going to describe their dimensions by their center of curvature and then also by their focal point. So the center of curvature, if I imagine a mirror like this, the center of curvature is just the radius of the mirror. Where is the center of the sphere from which that mirror was cut? So the center of curvature is the radius of the mirror. We're usually going to call that C. So R is the center of curvature. Or excuse me, let me not, I'm just going to call this C right now. C is equal to the center of curvature. And it is equal to the radius of that sphere. So in a problem, I'll give you what is the radius of the sphere, and then you'll know that that's the center of curvature. Something else is called the focal point, and that's more common to use the focal point. The focal point is equal to half the center of curvature. You've probably heard of focal point. Sometimes we also use focal length sort of interchangeably. Um, the focal length and focal point are a little bit different. Focal point describes this point in space, and focal length gives the distance from the mirror to that point in space. But in practice, they're the same. They're always going to be expressed as some distance from the mirror. So you can use focal point and focal length interchangeably, though, like I said, it's really just a technicality that they're different. But they're always going to be some distance from this place, from this mirror or lens. All right, so the focal point is half the center of curvature. Further, it's also the point where parallel rays converge, and rays are parallel when they originate from some source very far away. Like, for example, can you think of something that's really far away that puts out a lot of light? The sun or other stars, but the sun is very far away. And if you're close to the sun, light rays are not parallel, right? They emanate outwards in all directions. They're divergent. But as you move further and further away from the sun, if you move further and further away, then it comes to be that those rays that you're seeing when you're really far from the sun are basically parallel. You follow what I mean by that? Because you're only seeing a small sliver of the light that's coming from that object, and so they're basically parallel. I can also take an object, like I can even take a light bulb and just put it at the back of the room, and basically by the time the light gets over to me, all the way over here, I'm seeing only such a small portion of the light, of the sphere of light that it's emanating, that those rays are basically parallel. Now when these light rays come into a mirror that are parallel, they're going to all focus at the focal point. And so we describe the focal point in two ways. We describe the focal point as half the center of curvature, and then we also describe the focal point in a different way as the place where parallel light rays focus. And that's why we use the focal point, and that's why we call it the focal point, because it's where these parallel light rays focus. You need to know both of those ways because sometimes in problems I'll give you the center of curvature and you'll actually need to know what is the focal point. And so you have to take half the center of curvature. And then also we'll do some ray diagrams where you have to trace out the rays that are produced by mirrors or lenses. And you'll need to know this, that parallel light rays will focus at the focal point. By the way, what type of mirror is this? Is this a convex or a concave mirror? This is a concave mirror. I like to think, I don't know if I said this earlier, I like to think of a concave mirror. You know what it does? It caves in. It sort of caves in. It sort of looks like a cave, like you're walking into a cave. And then convex mirrors are not that way. Convex and concave, by the way, that describes only the geometry. So we'll see with lenses that lenses will be very similar to mirrors, but switched. We'll wait till we get there. But we'll use the convex and concave to still describe the geometry of the lenses, but not, it'll be different from the way that it affects the light. Well, you'll see when we get to it. Okay, now let's look at the mirror equation. It's going to be the same for lenses, so whatever you get here will carry over into lenses. You'll see that they're very, very similar, except with just a few small changes. This tells us how F, P, and Q are all related. Um, so the lens equation is 1 over F equals 1 over P plus 1 over Q. And then just to remind you, P is our object distance, Q is our image distance, and then F is our focal point. And further, don't forget that F is equal to the center of curvature divided by 2. What is the focal length for a flat mirror? What is the focal length for a flat mirror? Ever thought about that? Have you ever looked at your flat mirror and said, gosh, I wonder what the focal length is? Well, what is it? Uh, sorta, yeah. No, no. You're really sort of right in saying that there isn't a focal point. Because imagine a mirror like this, right? It has a focal point. What if I make it bigger like this? Has the focal point increased or decreased? It's increased. The focal point has increased, right? So if I imagine that I have a mirror like this, my focal point is, say, right here. But if I make the mirror uh, flatter, like this, now my focal point of the red mirror is somewhere over here. And if I continue to make it flatter and flatter and flatter and flatter, what is the focal point for a flat mirror? It just keeps getting what? Bigger or smaller? Keeps getting bigger and bigger and bigger. And so the focal length for a flat mirror is going to be infinity. That F for a flat mirror will be infinity. And so we can think about, well, 1 over infinity, well, that's equal to 0, right? And then let's go back and think about our lens equation, our mirror equation, or excuse me, our equation for flat mirrors was that P is equal to negative Q. So if I have 1 over negative Q and 1 over Q, then that's also equal to 0. So this mirror equation also works out for flat mirrors as well. Although we never use it for flat mirrors because it doesn't really make sense to, but it does work out for that. All right, so just a reminder of some of the things here for our sign notations, and that's going to be the big thing on this portion of the test is getting your signs right. That you need to remember when is P positive, when is Q positive, when is F positive or negative. So the object distance is positive if the object is on the sort of the front side of the mirror. All right, so when I talk about the front side of the mirror, what I mean is the side from which the light rays are coming. So here I have this mirror, light rays are traveling from me to the mirror, so this is the front side of the mirror. The back side of the mirror is like, you know, from Poltergeist, where those creepy people live. That's the opposite side of the mirror. And so this, if I'm standing on this side, my object distance is positive. But if some way I could stand on the back side of the mirror, then my object distance would be negative. That doesn't happen very often, but we'll see where it happens in one special case that we'll have to deal with. So usually the object distance is positive. Image distance, we've already seen this. If the image is in the front side of the mirror, that's a positive image distance. That's a real image. If it's on the back side of the mirror, it's negative. So positive, remember this is real, this is virtual. Uh, this is usually the case, so this is usual that P is positive. And then the focal length, if it's in front of the mirror, it's positive. If it's in back of the mirror, it's negative. What is the focal length for this mirror? This convex or concave? Wait, this is convex. Is the focal length positive or negative for this mirror? Is the focal point or the focal length on this side of the mirror or is it on this side of the mirror? This is the front, this is the back. Is the focal length positive or negative? That's right, because the focal point is back here. Imagine this was cut out of a sphere. The center of curvature of the sphere, I don't know, is right here. So the focal point is right here. So convex mirrors have a negative focal length. And then concave mirrors, which cave in, these mirrors, these have a positive focal point because my center of curvature is here. My focal length then, or my focal point, is right here. It's on the front side of the mirror, and so this has a positive focal point. I'm sorry, I wrote, yeah, this should be convex, and this should be concave. All right? It's important that you get those sign notations down. I think a note card would be really helpful. Just write down some of these things and carry it around with you and look at it a few times, and you'll get it in no time because it starts to make a little bit of sense as you move along. But just be familiar with them as you go throughout the week. All right, let's try this clicker question. Just want to remind you, I'll go ahead and write your equations over here. You'll have them on your equation sheet. 1 over f equals 1 over q plus 1 over p. And then our magnification is equal to negative q divided by p. That's all you need to know. And then something else I've told you is that f is equal to c divided by 2. Couple steps you'll need to do. First, you'll need to find out what is the image distance, and then you can calculate what is the magnification. If you finish this one, you can go on to the next one or the next one. You finish this one, go on to the next one. There are 3 here in a row. We'll do about, I don't know, 20 or 30 seconds left. All right, I'm going to stop at 245. Just guess if you're not sure. 245. There's some similar homework problems to these for good practice, and you'll probably see questions similar to these on the test. Uh, This is probably one of the easier of them. So let's take a look. I know they're still new, but with some practice, you'll get the hang of this. So what I want to look for here is the focal point, and I also want to figure out just sort of what I have. So first of all, the radius of curvature, it says, is 20 centimeters. That means that my focal point is going to equal 20 over 2, or 10 centimeters. By the way, I can keep all of my distances here in centimeters. I don't need to convert them to SI units. The units all cancel out in the end anyway, or they all work out in the end. And then also it says the object is located at 20 centimeters. I need to think, what does that mean? Is that P or is that Q? And should it be positive or negative or what? Well, is this object or image distance? That's my object. So P is equal to 20 centimeters because it tells me that's where the object is located. So now I want to know, what is the magnification? I know that's negative Q divided by P. I know P, so I just need to find Q. So I say 1 over F equals 1 over P plus 1 over Q. Working with these fractions can be difficult for some of you, I know, especially. But I try to give you nice, easy numbers that work out easily. Work through a few of them, and then you'll get the hang of dealing with these fractions. If you're having trouble, please come see me. 1 over F, that's 1 over 10, equals to 1 over 20 plus 1 over Q. And then I subtract 1 over 10, 1 over 20 equals 1 over Q. Define, you can do this in your calculator. I can say 2 over 20 minus 1 over 20. That's 1 over 20. So Q then is equal to 20. So if Q is equal to 20, then that tells me that my magnification is negative 20 divided by 20. That's Q divided by P. So it has a magnification of negative 1. All right? Oh, wait. No. Yeah, that's right. Magnification of negative 1. Another thing you have to be careful with on this is the focal point. It wasn't a problem here because my focal point for a concave mirror is positive, but I'm not always going to tell you. So for example, if this was a convex mirror, it would look largely the same, but you would have to take your focal point to be negative. With practice, don't worry, you'll get the hang of it. But whenever you answer a problem, you need to think about, what kind of device do I have, and does it have a positive or negative focal point? In this case, it was a positive focal point, so it worked out okay. So C is the right answer. Let's try the next one. This is also a mirror. There I give you the height of the object. Tell you it's placed 3 centimeters in front of the mirror. And then I tell you about the image. And now I want to know, what is the image distance. This one's a little bit more difficult. Think about sort of how those equations all interact with one another. You want to start this problem just by writing down everything you know. Writing down, what is this 2 centimeters? What is this 3? What is this 5? What does it mean that it's virtual? What does that tell you about the sign of the object? to about 20 more seconds. Finish this one, go on and do the next one. Although if you're doing the next one, make sure you realize that that's a convex mirror in this third problem. But for now, we're looking at this one. We'll stop in about 8 seconds. We'll stop at 245, 245. Just guess if you're not sure. Okay, we're still a little bit all over the board. Listen, you'll get the hang of these as we go along. Don't sweat it. But you do need to work through the homework, and we'll do some more practice in class. But your test questions will be very similar to these. So here, let's just go through and figure out what it is that I know. This is the object. So I know that HO is equal to 2 centimeters. And then I also know that HI is equal to 5 centimeters. All right. Now, what I don't know is this object inverted or is it upright? But I can intuit a little bit of is it inverted or upright because it gives me this information about it being virtual. Is a virtual image going to be inverted or is it going to be upright? Or can you tell? Is a virtual image inverted or upright? Remember our equation for magnification. Our magnification is negative Q over P. If an image is virtual, what does that tell you about its image distance? Does it have a positive or negative image distance? It has a negative image distance. So how does that affect the magnification? Because M is negative Q divided by P. If Q is negative, then M is what? It's positive. So that's one sort of rule that we can hang on to, that virtual images are always upright. Virtual images are upright. Real images are inverted. All right. Um, so here, I know this is an upright image, so my image height is going to be positive. Now, even if you didn't discern that in the beginning, that's not going to affect this problem. But if it turned out that this image was inverted, then you would get the answer wrong. And so we'll see some problems where it's very important that you do a little investigative work at the beginning to think about what types of images are being formed by these devices. Don't worry, you'll get the hang of it as we go along. But you just need to think about what kind of device you're using and what type of image it's forming. So it's 5 centimeters high and it's virtual. Because it's virtual, I know that that is positive and that Q is negative. So I'm going to go ahead and write down that Q should be negative some value. So by the way, I can go ahead and get rid of D. I know that D can't be right because Q has to be negative. All right, and I want to know the image distance. I can figure out M is HI over HO. So that's going to be 5 over 2 or 2.5. This mirror has a magnification of 2.5. And then I want to know the image distance. I also know that M is negative Q divided by P. Q then is negative M times P, which is negative 2.5 times P, which was given right here, 3 centimeters, and 2 times 3, 2.5 times 3 is 7.5. So B there is the right answer. Let's see, what did y'all put for A? Why'd you put 1.2? I'm not sure why you put 1.2. You might have a discernible reason for putting 1.2, or you're just guessing. I forget why I put that as an option. But here, B is the right answer. Let's see. We'll look at the next one. We're not going to have time to do it, but let me just give you a little bit of insight into the next one. Here I have a convex mirror. And with the convex mirror, we need to remember that a convex mirror always has a negative focal length. And the negative focal length means it has a radius of curvature of 2 meters. And so the focal point then is negative 1 meter. This is a convex mirror and it has a negative focal point. So that's not stated in the problem overtly, but it's something that you need to know as you move into it. We'll do some more practice on this, but this week, please do the homework questions. It'll help you prepare for the exam. And you can go back and look at some old optics questions from last semester, or you might need to go back to the spring. If you look at older tests, you can find them on the spring semester. It was last semester that I started doing optics. Well, you all have a good day. I'll see you.